take a deep breath in and a slow breath out. Simple, isn't it? The most fundamental act of life. You know, you hear yoga instructors emphasizing it all the time, saying focus on your breathing. It can soothe so many stresses.
That's true.
And think about it. An adult, someone like you or me, we breathe, 12 to 20 times every single minute? It's just constant.
It absolutely is.
Yeah.
Air is, well, quite literally life for every living being on this planet. But it's funny, isn't it? It's also something we just completely take for granted.
Completely. Maybe because we can't see it.
I think so. You can only really feel it, sense its power when it's moving, that moving air.
Yeah.
Well, that's what we call wind, of course.
Exactly. So today we're embarking on a bit of a deep dive. We're looking into this incredible invisible blanket that wraps around our Earth, the atmosphere. We've sifted through quite a stack of sources, scientific stuff, real-world examples, and we're here to sort of pull out the most important insights for you.
That's the plan.
Our mission really is to uncover what truly matters about the air we breathe, its intricate structure, its immense importance, and maybe especially the critical challenges it faces today. Let's really unpack this.
Let's do it. Because when we think of air, it's so easy to just picture it as one single thing. But what's fascinating from the research is that air isn't a single element at all. It's actually a complex mixture.
A mixture of different gases.
Precisely. Incredibly well balanced, too.
That's a really crucial distinction. And the proportions are quite remarkable. Leading the pack by a long way is nitrogen. It makes up a massive 78% of the air we're breathing right now.
78%.
Yeah. And nitrogen isn't just filler. Think of it like the atmosphere's natural fire extinguisher. It's vital for plant growth, obviously, but crucially, it dilutes the oxygen.
It slows things down.
Right, slows down oxidation. Without it, apparently, even a tiny spark could, turn the world into a giant bonfire.
A scary thought.
Yeah.
Then, of course, we have oxygen. That accounts for about 20.9% of the air.
Or the breath of life.
The breath of life, exactly. The vital gas we need for survival and also for burning processes.
Okay, now, here's where it gets really interesting, I think. Carbon dioxide.
Ah, yes. CO2.
Often seen as the bad guy in today's climate discussions, but it's also fundamentally life-supporting. And its proportion is surprisingly tiny, just 0.03%.
0.03%. It's astounding, isn't it? Such a minuscule fraction holds the key to Earth's temperature control. It's like a tiny valve on the planet's thermostat.
Wow.
And carbon dioxide isn't just used by plants for photosynthesis, which gives us food, It also has this unique ability to absorb heat. It helps keep Earth's temperatures moderate.
So it keeps things stable?
Very much so. Our research really emphasizes this. Without it, days would be scorching hot, nights would be bone-chillingly cold. Life as we know it, impossible.
That small amount makes that much difference.
It does. And it's also the heaviest gas in the air, generally speaking. So it tends to concentrate a bit more in the lower layers.
Is that why hill stations feel cooler?
That's part of the reason, yes. Less dense air overall higher up, and slightly less concentration of this heat-trapping gas compared to right at sea level.
That makes so much sense. Okay, so beyond these main gases, there are others in tiny amounts. Argon at 0.90%, and then everything else, just 0.17%. Helium, ozone, water vapor.
Tiny traces, yes. But it's not just gases, is it? The sources also mention non-gaseous things floating around up there.
Right, like pollen grains.
Crucial for seed dispersal, carry them over vast distances. And then dust particles.
Which seem like a nuisance when you're cleaning.
Huh, true. But they're absolutely essential for condensation. Water vapor needs something to cling to form clouds and eventually rain. So no dust, no rain.
Incredible. And salt particles, too, near the sea?
Naturally, yes. Picked up by the wind from the ocean surface.
Okay, so we've looked at what we're breathing, this complex mixture. Now let's look up, so to speak, and see how it's all organized. It's not just one uniform blanket, is it?
No, not at all. It's structured. Earth's gravity plays a huge role here. It holds the atmosphere close, making it densest near the surface.
And it gets thinner as you go up.
Exactly. And based on differences in, density and particularly temperature, scientists divide this shield into 4 distinct layers, each with its own job, you could say.
Let's journey through them then, layer by invisible layer. First up, our home layer, the troposphere.
That's where we live. It's the lowest, densest, and also the most turbulent part. It goes up to about 8 kilometers at the poles, but stretches higher, maybe 18 kilometers at the equator.
And it holds most of the atmosphere's actual mass.
The bulk of it, yes. And here's the really key thing for us down here. The troposphere is the only layer with significant water vapor and those dust particles we mentioned.
Ah, so that's why all weather happens here.
Precisely. Clouds, wind, rain, snow, storms. It's all happening in the troposphere, and its temperature generally decreases as you go higher.
The normal lapse rate, right.
That's the one. Roughly speaking, for every 165 meters you climb, the temperature drops by about 1 degree Celsius.
That's why mountaintops are cold even on sunny days.
Exactly. You need a warm jacket. And interestingly, the height of the troposphere itself changes slightly. It shrinks a bit in winter, expands in summer.
Because air contracts when cold and expands when warm.
You got it. Simple physics, really.
Okay, so this layer isn't just our weather factory, it's also like insulation. Shields us from extreme heat, holds warmth in at night, and the boundary at the top.
That's called the tropopause. So once you pass that, you enter the stratosphere.
The stratosphere, up to about 50 kilometers.
Roughly, yes. And this layer is known for being incredibly stable. Very calm.
No clouds, no storms.
Correct. Which is why commercial jets like to fly here. Smooth ride.
Makes sense. And inside the stratosphere, between maybe 15 and 35 kilometers up, there's something absolutely vital, the ozonosphere.
Yes, the ozone layer. Containing ozone gas, which acts as our planet's natural sunscreen.
It absorbs most of the sun's harmful ultraviolet or UV rays.
Almost all of them. Preventing them from reaching the surface and, well, causing a lot of damage. Life as we know it really depends on that layer.
So important. And temperature-wise, the stratosphere is different from the troposphere, isn't it?
It is. After about 20 kilometers up, the temperature actually starts to increase with height.
Increase. Why is that?
It's because the ozone gas is absorbing all that UV radiation from the sun. That absorption process releases heat.
Fascinating. And no horizontal air movement either.
Very little, very placid, as I said. The upper limit of the stratosphere is called the stratopause.
Okay. Beyond the stratopause, layer 3, the mesosphere, stretching up to about 85 kilometers.
That's right. And here, surprisingly perhaps, the temperature starts falling dramatically again as you go higher. It plunges to almost minus 100 degrees Celsius.
Minus 100, that's incredibly cold. It's the coldest layer.
It is indeed. Despite the cold, there are still some air motions here. And this is also where you see shooting stars.
Ah, meteors burning up.
Exactly. They're not stars at all, just space debris burning up as they hit our atmosphere at high speed, creating those bright streaks of light. The upper boundary here is the mesopause.
And finally, the highest main layer, the thermosphere. Starting around 80 kilometers and going way, way up to maybe 500 kilometers.
Or even further, depending on how you define it. And here, the temperature pattern reverses again. It starts to rise sharply.
How high does it get?
Very high, more than 1,500 degrees Celsius, due to the direct absorption of intense solar radiation.
Wow. And the lower part of the thermosphere has another name, doesn't it? The ionosphere.
Yes, the ionosphere. It's called that because it contains lots of electrically charged particles, or ions.
Ions. How do they get charged?
The sun's powerful radiation, especially UV and X-rays, knocks electrons off the gas atoms and molecules up there.
And these ions are important for us.
Critically important for radio communication. They act like a giant mirror in the sky, bouncing radio waves back down to Earth. That's what allows for long-distance radio broadcasts.
Amazing. Like an invisible communication highway. And the very top layer.
That's the exosphere. It's really the fringe, sort of blending into outer space. It can extend thousands of kilometers out, maybe up to 10,000 kilometers. Very, very thin air, extremely low density. And temperatures can get incredibly high, notionally up to 4,500 degrees C, though it wouldn't feel hot like we experience heat because the density is so low.
What an incredibly complex system, layer upon layer, each with its own unique features and functions. It really makes you think, what would life be like without this whole structure? Why is it all so indispensable?
Well, it's fundamental, isn't it? If you connect the dots we've discussed, nitrogen is essential for soil fertility, plant growth. Oxygen, well, we need it to breathe, obviously, but also for any kind of burning.
And carbon dioxide, that tiny fraction, is needed by plants for photosynthesis, creating food, and it regulates the planet's temperature.
Precisely. Then there's ozone, our silent guardian against UV rays. Even those tiny dust particles, crucial for clouds and rain.
And the air itself allows sound to travel, helps transfer heat around the globe.
Maintaining Earth's overall temperatures in a range that supports life. Without this whole intricate system working together, life just wouldn't be possible here.
Which brings us, unfortunately, to a really critical, urgent topic. The greenhouse effect and global warming.
Yes. The sources use some helpful analogies. Think of a glass house in a nursery.
Right, a greenhouse.
Sunlight, the heat and light, passes easily through the glass. The plants love it. But the heat radiated back from the plants and the soil gets trapped inside by the glass. It can't escape easily, so the inside warms up.
You get the same effect parking your car in the sun, don't you? The inside gets much hotter than the air outside.
Exactly the same principle. Heat gets in easily through the windows, but struggles to get back out. That's the greenhouse effect in action on a small scale.
So what does this mean for the whole planet?
Well, the issue is that human activities primarily burning fossil fuels like coal, oil, and gas for energy, plus rapid industrialization and emissions from all our vehicles are releasing huge amounts of extra greenhouse gases into the atmosphere.
Gases like carbon dioxide.
Carbon dioxide is the main one, yes. But also others, like methane, nitrogen oxides, and something called chlorofluorocarbons, or CFCs.
Ah, CFCs. Weren't they used in old fridges and things?
They were, yes. Widely used in refrigerators, air conditioners, aerosols, even some aircraft processes. They're very effective refrigerants, but they also trap a lot of heat. You can feel the heat coming off the back of an old fridge.
Right.
So these extra greenhouse gases in the atmosphere act like they're greenhouse glass or the car window. They let the sun's energy in, warming the Earth's surface. But then they trap more of the heat that radiates back from the Earth, preventing it from escaping into space.
So the whole atmosphere gets warmer.
That's the essence of global warming. We're thickening the planet's natural heat blanket, trapping more heat than is natural.
And it's made worse by deforestation, isn't it?
Absolutely. It's a huge contributing factor. Trees are amazing because they absorb carbon dioxide. They take it out of the air for photosynthesis.
Natural carbon sinks.
Exactly. But we're cutting down forests at an alarming rate for farming, building houses, roads, factories. So we're reducing the planet's ability to absorb CO2 at the same time as we're pumping more of it into the air.
It's a real double whammy.
It really is.
And this also connects to another major atmospheric problem: ozone layer depletion.
Yes, they're linked, though distinct issues. We talk about how vital that ozone layer in the stratosphere is, filtering out harmful UV rays.
Our natural sunscreen.
Well, unfortunately, that protective layer is getting thinner in places. Scientists detected a significant thinning, often called the ozone hole, particularly over Antarctica.
What's causing that?
It's primarily caused by increased levels of certain chemicals reaching the stratosphere, especially those CFCs we mentioned, and other related compounds.
The ones from fridges and aerosols.
Yes, among other sources. Though they've been largely phased out by international agreements, they persist in the atmosphere for a long time. Other factors contribute too, like certain industrial emissions, and even large volcanic eruptions can temporarily affect ozone levels by releasing sulfur dioxide high up.
And the consequences of a thinner ozone layer
Are very serious. More harmful UV radiation reaches the surface. This directly increases the risk of health problems for us, especially skin diseases, including skin cancer. It can also harm plants and marine ecosystems.
So we have global warming trapping heat and ozone depletion letting in harmful radiation. What are the wider impacts of the warming itself that we're actually seeing?
The impacts are already widespread and quite alarming. We're seeing glaciers melting at an accelerated rate all over the world.
Which contributes to sea level rise.
Yes, along with the thermal expansion of water as it warms. We're also seeing significant changes in global rainfall and snowfall patterns. Some places getting much more rain, leading to floods, others facing severe droughts.
And that affects farming.
Absolutely. Changes in weather patterns impact agricultural yields, which raises concerns about food security globally.
And the rising sea levels.
That's a huge threat. It endangers low-lying coastal areas, major cities built near the coast, and entire island nations could eventually be submerged.
It's devastating to think about. And health impacts too.
Yes. Beyond the ozone issue, warming itself can exacerbate certain conditions. Heat waves become more frequent and intense, leading to heat stress and related illnesses. Mosquito-borne diseases might spread to new areas as temperatures rise. And generally, higher temperatures, especially in tropical regions, just lead to more discomfort.
Which, perhaps ironically, means people use more air conditioning.
Which uses more electricity, often generated by burning fossil fuels, further contributing to the problem. It's a difficult cycle.
There's a really stark example of this warming in the research, isn't there? Longyearbyen in Svalbard.
Yes, Svalbard, the world's northernmost settlement. And it's home to the Glober Seed Vault,
The Doomsday Vault, storing seeds from all over the world.
a vital backup for global agriculture, holding samples representing thousands of years of farming history. But the issue is, Longyearbyen is warming incredibly fast.
How fast?
It's considered perhaps the fastest warming place on Earth. Its average temperature has gone up by about 3.7 degrees Celsius since 1900.
3.7 degrees, compared to the global average of about 1 degree.
Exactly. More than 3 times the global average. This rapid warming is making the region warmer and wetter.
And that's bad for the seed vault.
It's a serious problem. The vault relies on the surrounding permafrost, permanently frozen ground, to help keep the seeds inside frozen, even if the artificial cooling systems fail. But the permafrost is starting to thaw. There was even an incident a few years ago where meltwater seeped into the entrance tunnel.
Wow.
They've since reinforced it, but it highlights the vulnerability. This treasure trove of biodiversity, designed to last for centuries, is being threatened by the very climate change it might be needed to combat one day. It's a real
wake-up call.
It really is. A stark reminder of the urgency. But importantly, the sources also talk about solutions. There are things we can do to reduce global warming.
That's crucial. What are the key actions?
Well, one of the most vital things is to increase forest cover. And importantly, not just planting seedlings for a photo opportunity, but genuinely caring for them, protecting forests, allowing them to grow and mature so they can absorb significant amounts of CO2.
Reforestation and afforestation.
Precisely. Then drastically reducing emissions from vehicles is key.
How?
Shifting to public transport, promoting electric vehicles. Look at Norway, where nearly 60% of new cars sold are electric now. That's incredible.
Amazing progress.
Also carpooling, using cleaner fuels like ethanol where appropriate. Every little bit helps.
And replacing harmful chemicals.
Right.
Like those CFCs.
Yes. That's largely been done for new appliances, thankfully, thanks to international agreements like the Montreal Protocol. Switching to more eco-friendly alternatives in industry and consumer products is vital, and energy efficiency makes a huge difference.
Like using LED lights.
Exactly. They use far less energy than old incandescent bulbs. The example of Indian Railways replacing all their lights with LEDs is fantastic. A massive network making a real impact.
Simple changes, scaled up.
Yes. Encouraging cycling for short trips is another one. Good for health, good for the planet.
And shifting our energy sources.
Fundamentally, yes. Moving away from fossil fuels towards renewable energy, solar power, wind power. And safely managed nuclear power is also part of the low-carbon mix for many countries.
It feels like a huge challenge, but there are success stories. Bhutan, for example.
Bhutan is incredible. Our research highlights that Bhutan is actually carbon negative. It absorbs roughly 3 times more carbon dioxide than its entire country produces.
3 times more? How?
Mainly due to its vast forest cover, which is protected by law, and its reliance on hydropower. It shows what's possible with strong environmental commitment.
That's truly inspiring. And on a global scale, there was the Paris Agreement in 2015.
Yes, a landmark agreement where nearly 200 countries pledged to work together to limit global warming to well below 2 degrees Celsius, preferably to 1.5 degrees compared to pre-industrial levels.
So collective action is happening even if progress feels slow sometimes.
It is happening. These examples, from Bhutan's national policy to the global Paris Agreement, show that change is possible when there's the will.
So we've covered a lot today. We've journeyed through the atmosphere's composition, its amazing layered structure, and just how vital it is for absolutely everything.
And we've also looked squarely at the serious challenges: global warming, ozone depletion, understanding the causes and the impacts we're already seeing.
But we've also seen there are solutions, pathways forward, from individual actions to national policies and global cooperation.
Steps that are being taken and steps we can all contribute to move towards a healthier planet.
Which leads to a final thought. Considering Bhutan's incredible achievement of being carbon negative and that global commitment made in Paris, what role do you, listening now, see for individual actions combining, scaling up to help create a truly breathable, sustainable future for everyone?